If I tighten this any tighter, we're going to be into the preload territory, which is where we want to be, except it doesn't take very much at all to exceed the maximum preload. Now, by the way, I made that look easy, but when we have a crush sleeve in here and we have to tighten that nut down and get to this same point, you're going to have to start crushing this crush sleeve. And the service manual tells us it can take up to 350 foot-pounds of torque to start this crush sleeve crushing. And it's hard to tell, and it's real easy to lose patience and go too far when you've gone, or it's hard to tell if you've got the preload set correctly, because it's so hard to turn. So you've got to have patience and turn the nut just a tiny bit at a time while you're crushing the crush sleeve for the last time. And I'll demonstrate it for you. Hopefully I can do it without ruining the crush sleeve and having to use it or reuse it by going too tight. If you go too tight, the crush sleeve's no good and you got to replace it. But right now we are just doing an experimental setup to see if our pinion depth shim is correct. So the instructions would tell us at this point to check the bearing preload, and this old tool here actually has 3 little notches in it right here. Those 3 little notches, that center notch is exactly 12 inches from the center of this pinion shaft. And in the old service manual, the way they measured foot-pounds of rotational torque was, here's the foot, a 1 foot length, and then they used a spring scale, like a fish scale, to hook on there and pull, and there should have been so many pounds, 15 to 25 pounds of pulling force to at the 1 foot mark to pull this around, and that is the same as foot-pounds. But of course we have torque wrenches, dial style torque wrenches today that I'm sorry, not foot-pounds, inch-pounds is what it should be. We have real nice torque wrenches today that can do that, but there's no reason you couldn't do that same thing with a fish scale today. The principle is the same. Okay, well, I can tell you right now that we don't have we don't have enough preload, so we're looking for 15 to 25, I believe. I'm going to tighten this just a tiny bit more right there. I only, if that was a 32nd of a turn of the nut, I would be surprised. And by the way, every time you tighten down roller taper bearings to preload them, you need to rotate the shaft that they're on to settle those bearings, to seat those bearings. Now I'm feeling some resistance to rotating this. Notice it doesn't just freely rotate like it did before. So we've got some preload on there. The question is how much? Well, I don't know. I need to get my inch-pound torque wrench out and see. Okay, I've got my dial style inch-pound torque wrench. This measures from 0 to 30 inch-pounds, and it will record the maximum that it reaches. It has a max recording feature. So I'm going to just simply put this up on the nut and rotate it around, because on this model it's the constant rotational torque that we're interested in and not the breakaway torque. Some models though, it's the breakaway torque, so you need to pay attention. Okay, the max dial that it shows here. Let's see if I can get that to focus. Is it's on the black scale there. Let's see if you can read that. Right there is on 15 exactly. Now the specification for bearing preload on new bearings is 15 to 25 inch-pounds of rotational torque. So I lucked out. I hit it right on 15, but anywhere in that 15 to 25 range is good. And it does give us some physical resistance to rotating the pinion. If you recall, when we took this thing apart, it had 3 inch-pounds of rotational torque. So now we've got 15. So if we're that lucky when we put it back together with the crush sleeve, we will take it. But we just temporarily put this together to check to see if the pinion depth shims that we installed, the 28,000 shims, are the correct ones to put in there. So now that we've got the pinion installed and the pinion bearing preload set correctly, and once again, the preload keeps the pinion gear rotating on a smooth center line. It doesn't let the gear flop from one side to the other during acceleration or deceleration. So now we're going to turn this housing over, and we're going to take our differential case and its bearings and set them in here next. So let me grab the differential case here. Very heavy, of course. And we will lubricate these bearings after we put them on. I'm going to carefully, without dropping it, set this down in place, just like that. And I'm going to take the adjuster sleeve, the threaded adjuster. Notice it has threads on it, and it has these holes in the outside. And this tool right here is called a spanner wrench. It has these 2 little notches on it. Those notches fit into these holes and allow us to rotate this adjustable spacer. So we'll set that in and make sure that it rotates, and it does. We'll take the other bearing cup from the other side. Oops, I didn't lock that down. There we go. And we'll set it in on its bearing and put the other threaded adjuster on the other side and get it threaded into place. And I'm going to make sure that you have bearing backlash or gear backlash. So backlash is this right here. That's the spacing between the pinion gear teeth and the ring gear teeth. And the backlash needs to be, when we put a dial indicator over here on the gear tooth, it needs to be between 5 and 7 thousandths of an inch. Well, I can tell you right now, that's way too much backlash. So we have to move the ring gear closer to the pinion. So, excuse me, the way we do that is we loosen this threaded adjuster. Let's just take it a 1/4 of a turn. Uh-oh, got the tool stuck in there. 1/4 of a turn. And then we'll tighten this other side a 1/4 of a turn. And then check the preload or the backlash. Still too much. And so that's the process you go through. You keep adjusting the threaded adjusters until you get just a little bit of backlash. There. That's closer right there. Now, the spacer, the threaded adjuster spacer here on this side is what controls backlash. The adjuster on the other side controls bearing preload. Now, in order to actually do an accurate measurement of preload on these side bearings, I'm going to have to put the differential bearing caps on and get them torqued down to specification. And I always like to get the backlash reduced down to something reasonable. Not, you don't want huge amounts of clunk, but I'm not putting a dial indicator on it yet, because as soon as you put those bearing caps on and pull it down, the backlash is going to change anyway. It usually tightens up. So I'm going to put those bearing caps on. When we put the bearing caps on, you got to be real careful, because they also have the threads for that threaded adjuster that needs to be lined up. Now, remember, we made our paint mark on it, and there's the blue factory paint mark. My paint mark got cleaned off when I sandblasted this case, but the blue mark is still there. But we need to be real careful and make sure that when we put the bearing caps down all the way, that we're lining up those threads, because I've seen students miss the threads and get it, the threads okay in the bottom, but on the bearing cap they were cross threaded, and then they tightened the bearing cap bolts down, and it caused some severe damage. So it takes a little bit of practice to find the right threads to get that lined up. But I will take some time here and get those lined up and torqued down, and then we will go through the checking the side bearing preload and backlash next. Okay, just a little trick here to get these caps lined up. If you'll start the bolts first with the cap in the up position and have the adjusting sleeve here loose, so it's not tied against the bearing, then you can take and just lightly tap down on that side bearing cap and get it to drive all the way down. And you can tell if you are if everything's lined up, because the threaded adjuster will still spin when the cap is down. And that adjuster should always be adjusted to where there's a notch lined up with this hole that this lock plate bolts in place and holds the adjuster from moving. Now, of course, tightening down the bearing cap also makes it very difficult for that to turn, but it's just kind of a secondary lock there. So I'm going to tighten or take these bolts down to where they're almost torqued, and then we'll go through the instructions in the service manual for the proper setup of these adjuster sleeves. Okay, let's go through the proper setup on these adjuster sleeves. The service information tells us to back off the right hand adjusting nut and then tighten the left adjusting nut with the spanner wrench while turning the ring gear. Continue tightening the left hand nut until all lash is removed, and then lock the left hand nut in place by tightening the left hand bearing caps to 70 to 75 foot-pounds. So here's the right hand side, here's the left hand side. They want us to rotate the ring gear while tightening the adjuster sleeve on this side until all lash is removed. Right there. There's no lash at that point, and so the next thing it tells us to do then is to tighten those bearing caps down to 70 to 75 foot-pounds of torque. So let me get this set on 75. Actually, we'll do 70 just to there we go. 70 foot-pounds. Okay, so there's 70. And 70. All right, then next step is it says to tighten the right hand nut to force the left bearing firmly into contact with the left adjusting nut, and then loosen the right hand nut again, and then again tighten snugly against the bearing. So so tighten this side. Tighten this side firmly into contact with the left adjusting nut. Tighten the right hand nut to force the left bearing firmly into contact with the left nut. Then loosen the right nut again. So there's firmly right there. So then we'll loosen it. And then it says to tighten it again snugly against the bearing. Right there. Okay. Then it says tighten the right hand nut to a minimum of 2 additional notches to a maximum of 3 notches to a locking position. This operation preloads the differential bearings. So right now we have this hole lined up with our locking nut pretty close, but it tells us to go 2 more two more notches. So there's one. Man, I'm not sure if I'm tough enough to do a second one, but we have to. We've got to have the bearing preload for the side bearings set properly, and it helps to rotate those bearings. I did pour some lubrication in those bearings, so they do have lube on them. And let's try going another notch here. Oh, we're moving the whole table. I've almost got it. Real close. All right, let's bring the table back. I've got it turned 2 more notches from where it was, and that should add enough preload or squish on these side bearings that we can now turn the whole differential housing over and measure the total turning preload. Oh, except then we gotta lock these down to the 75 or 70. Get the torque wrench turned back on here. Okay, here we go. Here's the one. There's the other one. All right, so we're going to turn this housing over now. And remember, we have no seal, no crush sleeve. This is just a mock-up, a trial run of bearing preload, and we do have some backlash, but we're going to adjust the backlash here in a minute. But we don't even care about backlash at the moment until we measure the total turning preload, which should be more than the 15 now, because we've added the side bearing preload. And once the preloads are set correctly, then we can adjust the contact or the backlash, and then we can paint the teeth and run a contact pattern check. Okay, I've got the inch-pound torque wrench, and we're ready to measure the total turning preload. And remember, we had 15 inch-pounds of rotation just on the pinion, but now we're going to expect the preload measured here to go up because we've added the preload from the side bearings. But one thing you need to realize is that we are turning the pinion, which turns the ring gear, but this has a 3.36 turn of the pinion to 1 turn of the ring gear ratio, 336 to 1. And so the preload that we are actually going to measure here on the torque wrench is going to be 3.36 times lower than the actual side bearing preload because of the gear reduction. So let me zero our torque wrench here. We're going to rotate it around. Feels a little bit tighter. And remember, we had 15 before, but now we are on 23. I don't know if you can see that, but we're on 23. So we had 15 to begin with. Now we have 23. The difference between 15 and 23 is 8. And that's what we are picking up as the side bearing preload. But that's been reduced and made easier by a factor of 3.36 to 1, the gear ratio. So we're going to take 8, which was the difference between the 15 and the 23, multiply it by the gear ratio, 3.36, and we get 26.88 inches of preload as the side bearing preload. Now the specification for side bearing preload is 25 to 35 inch-pounds. Well, we're at 26.88, so we're right on the money. We've got the pinion bearing preload set at 15. We've got our side bearing preload set at 26.88. Both of those are well within specification, and that means now we can turn this thing over and set the backlash, and then set the or paint the gear teeth and run a contact pattern check. So let me get a dial indicator set up here so we can measure the backlash. The plunger of the dial indicator needs to be at a right angle with a gear tooth. So if you look at these gear teeth here, the best place to get a right angle with a plunger is right over here. You just bring the plunger in on this side. You've got a nice flat surface, and we can move the gear back and forth and measure the backlash. Notice on the other side, there is no right angle. And so you've got to be on this side of the gear tooth. So let me get that dial indicator set up. All right, I've got the dial indicator set up, and I've got the plunger of the dial indicator sitting on just one of the gear teeth here on this 336 to 1 gear ratio setup, and I'm going to measure the backlash on that particular tooth. You need to keep in mind this is just the backlash measured at this point that represents the actual gear contact of the gears, the ring gear versus the pinion gear down inside of here. So it's not really this tooth that we're measuring the backlash of. It's the contact that takes place down inside, but we can't get to that, so we're going to use this, or we're going to measure this backlash, or measure the backlash on this tooth right here. So let's measure that backlash first. The specification in this 1963 manual is 3 to 10 thousandths of an inch, with 5 to 8 preferred, and we're going to shoot for 6 or 7 as our adjustment. So right now, the dial indicator, as you can see, I've got it on 0, and let me just pull it back the other way. We've got this play right here. That looks like 8.5, 9 thousandths of an inch. So that is within the 3 to 10, but it's not in the preferred 5 to 8 range. Now, at this point, some technicians would think, okay, we're done. But you need to realize something about these gear teeth, and that is the manufacturing process. These gears right here are what are referred to as face milled gears. And face milled gears have out here on the outside edge, which is called the heel, the tooth depth is deeper at the heel on the outside than it is at the toe here on the inside. If you measure the tooth depth, it's shallow here at the toe and deep at the heel. These teeth are cut one tooth at a time. And so to say that because the backlash is good on this one tooth, that all of the teeth are good is naive. We don't know what quality of gears these are. We don't know what quality of machine work was done on these gear teeth. But it's been my experience that it only takes one gear tooth with no backlash to cause a vibration. Or don't forget, these gears heat up as you're driving down the road. As they heat up, they expand. And so if you had pretty low backlash on one tooth, but then not on others, as the gears would expand, they may expand and the backlash would actually get smaller, and they might actually bind. So the correct way, especially on a brand new gear setup like this, and students laugh at me, technicians laugh at me all the time for this, the correct way to do this is to physically measure the backlash on every single tooth. And there's a specification called backlash variation, and that variation should be no more than 2 thousandths of an inch. So 2 thousandths of an inch is the maximum difference between the backlash of the highest reading and the lowest reading on these gear teeth here. Now don't forget that our differential case that we had to machine in the brake lathe has 2 thousandths of an inch of back and forth lateral movement. And of course that's going to affect the backlash also. So we had, let's see, 8.5 thousandths on that particular gear tooth. Let's move to the next one. Right there. I am going to just zero the dial indicator at that point and pull it back. And I've got 9.5. So we've already gone from 8.5 to 9.5. We've got a 1 thousandths difference just from that tooth to the next. Okay, so let's go to the next gear tooth. Here we go. I'll zero the dial indicator because I turned it clockwise. Now I'm going to go back the other way. It's 8.5. So now we go to the next one. Zero it. Pull it back. And here we've got 7.5. And you see the process. I'm not going to make you watch me check every one of these, but we are going to look for a difference of no more than 2 thousandths of an inch from one tooth to the next. If we do have more than 2 thousandths of an inch difference from one tooth to the next, either we have too much wobble back and forth, the lateral run out in our case, which we've machined as true as we can get it, or we've got a mismachined set of gears. Now what I would like to do is let's turn this ring gear half a turn now and measure on the other side. So let's take this gear right here, because we had 2 thousandths of an inch run out lateral run out in the differential case, rotating the case half a turn might give us a different reading. So let's see what we get here. No, we still get 8.5. Oh, actually, I marked the high spot on the back of the differential case over here. Let me rotate that around. Right. All right, this was the high spot of run out for the differential case, right there. And that gives us 8.5 thousandths of an inch backlash. And here's the low spot of the run out right here. So let's zero the dial indicator at that point and pull it back. And we've got 9. So it looks like as long as the gear teeth are all machined equal depth, which is a huge assumption, that the run out, the lateral run out in the case, the 2/1000ths of an inch, is not going to be much of an impact. As a matter of fact, at the most, it would be half of that. So I'm going to pause the video for a moment while I check the backlash variation, and then we'll come back and discuss the results. And then the next step after that is to paint the gear teeth and run a contact pattern check to determine. Remember, we did all of this. This is just a preliminary test setup to see if our pinion depth is correct. Okay, I've finished checking the backlash on every single tooth. The lowest amount of backlash was 7/1000ths of an inch. The highest was about 9.5. So technically we're about a 0.5 thousandths too much, because the specification is 2/1000ths of an inch. But we are going to live with that. That's just fine. Okay, so our next step is to run or paint the gear teeth and run a contact pattern check. Well, you should never ever paint the gear teeth and run a contact pattern check until several things have happened first. Number 1, your pinion bearing preload is set properly. Number 2, your side bearing preload is set properly. Number 3, your backlash is within specification. Now, we are within specification, we're just not within the preferred specification. And interestingly enough, the contact pattern check will tell us if our backlash is too wide, which I think it is, or not. And it'll also tell us if our pinion gear is too high or too low or just right in the case, just by looking at how the gears contact each other. So those three things, the preloads and the backlash, have to be set properly first before we can paint the gear teeth and run the contact pattern check. So I'm going to get the contact pattern paint and get painting these next. Okay, the gear marking compound I'm going to use is not the compound that came with this gear set. This is the little container of gear marking compound that came with the gear set, and it's just a little tiny bit. And that little tiny bit is not enough for what I do, and that is that I paint every single gear tooth, both on the drive side and the coast side of the gear teeth, and we'll talk about those here, which one is which and how to read them. But they really only give you this little tiny amount of contact pattern grease, because in most service manuals and most training organizations and most technicians think that all you got to do is paint a few of the gear teeth and all the other gear teeth will be exactly the same. Well, that's simply not the case. You can get a variation in your contact pattern that can come from mismachined gears that you want to make sure that you've got a consistent, steady pattern. So I've just got a larger can of it here. This particular can is from Mopar, but I like it because it comes with a little paintbrush right there, and so I'm just going to come in and I'm going to paint the coast side. So this is the coast side right here of every gear tooth. And yeah, we'll have to rotate it around to get the rest of them. I'm also going to paint the drive side. This is the drive side right here. So I'm going to paint the coast and the drive side of every gear tooth. You don't need to glob it on, but it does need coverage so you can see the pattern where the gears contact each other. By the way, wear some nitrile gloves or latex gloves as you do this, because this stuff is messy. It gets all over your hands, and then you wipe your face, and it gets on your face and all your clothes, and it and it doesn't like to wash out either. So, and once we get all these painted up and run our contact pattern check and get everything adjusted properly, then we'll use some brake spray cleaner and wash all this off of here. It won't hurt to mix with the oil, but it turns the oil orange, and that a lot of guys don't like orange oil. There'll be a little bit of orange anyway, but the break-in procedure on a new set of gears is at 500 miles you change your axle oil. And the reason for that is new ring and pinion gear sets are lapped together with a special gritty lapping compound, sometimes called lubrite. And that compound can be stuck to the gear teeth, and as you drive the vehicle with the gear oil and everything heats up and cools down, it washes that lubrite down and towards the bottom of your differential housing, and then you can, when you change the oil, it can come out. And they do that on purpose so that during the first 500 or so miles of driving, it helps establish a wear pattern between the ring gear and the pinion gear. Now, the proper way to run a contact pattern check, now that I've got the gear teeth painted, is to somehow put a load on the ring gear to try to prevent it from just easily spinning while you turn the pinion gear. And if I had somebody here to help me, I would do that. But since I'm just here by myself, well, what I would normally do is take a pry bar and just kind of wedge it between the housing and the gear to make it more difficult to turn, and then have somebody else turn the pinion gear. But I'm just going to give it some resistance by hand and turn. So we're getting a pattern on the coast side. Now we're going to go back the other way and get a pattern on the drive side. We are lucky. We are really lucky. Okay, and you want to rotate it at least 4 times in each direction, or at least more than the gear ratio. This is a 3.36 to 1 gear ratio, and we want to turn it so enough that every single tooth on the ring gear gets some contact. So now let's zoom in and look at these gears on their contact. And let me get a little pointer so my big fat finger isn't in the way. Okay, I want to show you how to interpret the contact pattern, see what it's telling us. And so let's come in over here on the coast teeth first. So this side, the convex side of the gear tooth, is the coast side of the tooth. And notice we've got a dark contact area that's pretty centered. Outside here is the heel, on the inside is the toe. If you could imagine a line dividing the upper and lower portions of that gear tooth, that would be called the pitch line. And then anything below the pitch line down deep inside, that's called the flank. And anything up towards the top here is called the face. Well, you want your contact pattern kind of centered in that area. And this one we've looked out is centered very well right in that area. So now let's look at the coast side of the tooth. The concave side here is the coast side. And the coast side, notice its dark area is centered in the tooth. Now, one that wouldn't be centered would be if this dark spot came all the way off the edge of the tooth. You don't ever want this dark contact pattern coming off the toe or the heel. If it does, then your gears are not set up correctly as far as backlash or pinion depth. And there's an easy way to tell. There's there's 5 different contact patterns. We lucked out on this one, and we have a nice centered pattern on the coast and a nice centered pattern on the drive side of the tooth. But that's really unusual to be able to just put it together like that and get that good of a pattern. So let me zoom in here just a little bit more and show you what kind of patterns you can get. The first 2 patterns I'm going to describe to you are hopefully the ones that you see, because they're the easiest to fix. And that is if on the drive side of the tooth, this convex side, the contact pattern was out here towards the heel. Whoops. Let's do that. Let's look at I was out of the screen there. Sorry about that. Let's do that again. So here on this concave or convex side of the tooth, if this dark pattern were out here on the heel, on the drive side here, and also on the heel on the coast side, so I call that a heel-heel pattern. That tells us the backlash is too wide, and you would need to adjust the backlash. If the pattern was too dark, or was dark down here on the toe on the drive side and the toe on the coast side, then that tells us the backlash is too tight. Now on this axle, that's an easy thing to adjust. These threaded adjusters here, to adjust backlash, these notches, these holes here that have to line up with the locking tabs, if I wanted to move the ring gear away from the pinion, so the pinion's right down here, but if I want to move the ring gear away from the pinion to increase backlash, I would come over here on the opposite side on the threaded adjuster on the other side, and I would back it off, say maybe 2 or 3 notches, and then I'd come over here on this side and tighten it 2 or 3 notches. By backing off on the one side and tightening on this side equal amounts, you will maintain the bearing preload as you should, but it will also move the differential case over and bring the ring gear farther away from the pinion, which increases backlash. And obviously the opposite is true if you want to decrease backlash. We would loosen this one a couple of notches and then tighten the other one a couple of notches, and that would bring the ring gear closer to the pinion. Hopefully that's all you'll ever see, but that has not been my luck. I can't believe the luck we have on this axle. Now let's talk about the kind of luck you don't want to have, because it's called bad luck. And the bad luck can occur when on the drive side of the tooth, so drive side of the tooth right here, if the pattern were heavy on the heel, but on the coast side it was heavy on the toe, that's a pinion depth problem, and the pinion gear is too far down in the differential case. If just the opposite were true, if it were towards the toe on the drive side and towards the heel on the coast side, then that tells us that the pinion depth is too high. And in all of those situations, you're going to have to take that pinion gear back out and change the pinion depth shim to something thicker or thinner, depending on if you want to raise or lower the pinion gear in the differential housing. So that's a lot of work. That's why we did not put a crush sleeve in or an oil seal, is because we weren't sure if we were going to have to change the pinion shim again. Well, we don't have to. So now we're ready to reassemble this axle. Of course, we'll have to disassemble everything that we've already put together. We've got to take these bearing caps off, get the differential case out, take the pinion nut back off, pull the flange off, take the pinion gear out, and then put the crush sleeve and the pinion oil seal back in and set everything back up exactly how we have it. We lucked out. The backlash apparently is perfect at the 7 to 9 thousandths of an inch that we've got it at. The pinion depth shim at 28 thousandths of an inch is perfect. Otherwise, our pattern would have showed us that the pinion depth was wrong. So I have to tell you, in 23 years of teaching axles, I have never had one that's set up perfect like this. Never. It just doesn't happen. I wish that it did not happen, because then I could show you some of the changes that needed to correct an incorrect contact pattern. But always pay attention to the contact pattern, because the contact pattern is the final say of whether your backlash needs to increase or decrease, or your pinion depth needs to increase or decrease. So I'm going to disassemble all this and get it ready to go back together. I will show you how to crush the crush sleeve and put that together, because it's very difficult, and most technicians will use an impact gun, and that is an improper way to do it. You'll damage bearings, and you can easily over torque the pinion nut, crush the crush sleeve too far, ruin bearings, and then have to start all over. So let me get that set up. Okay, I have removed the differential case with the ring gear. I've removed the pinion gear that I've got right here, and if you recall, we had this put together for kind of a trial run to make sure that our bearing shim for preload, or not preload, pinion depth in the case was correct, which we verified that it was by our contact pattern, and that our backlash was correct at the 7 to 9 thousandths of an inch. So if we had installed the crush sleeve initially, at least on that build, it would have been fine. We would have gotten away with it. But most of the time, you're not. Well, I wouldn't say never, but that's not going to happen very often. So we've got this crush sleeve that we now have to put on the pinion gear, and that's going to sit in between the two bearings. And this time I'm going to use the new pinion nut. It's a locking nut, and we'll put some thread locker on it also, just to make sure that it stays in place. And we are also going to install our pinion shaft oil seal, and then put this thing together hopefully for the final time, and get it all set up and ready to put back in the vehicle. So to start with, we're going to take this pinion bearing, the front pinion bearing. It's already lubricated. We're going to put it back in the differential housing here, and we're going to install this seal. Now, when you install a seal, it's not a good idea to take a hammer and just try to knock it in. If all else fails, get a 2x4, a piece of wood or something to drive it in evenly. Here at the university, we have the actual special tool from General Motors to install this tool, or to install this seal. But the thing we do not want to happen is on the inside of this seal, we do not want this little spring called the girdle spring. We don't want that spring coming out after you've knocked it in place. So we're always going to look inside after the seal's installed. A little piece of crud there. And make sure that that seal hasn't fallen out, because sometimes it'll fall out when you knock it in with a hammer. So it's easily put back in. It's just a little groove that it sits in. But we're going to take, and I almost always use a brass hammer, so that when I'm hitting something cast iron or steel, the hammer is softer and it's less likely we're going to damage the part that we're hitting. And so let's drive this seal in. We just keep it nice and centered, and whoa, I better get the pinion off of here before it falls on the floor and breaks a tooth. That wouldn't be good. Okay. Okay, we're almost down flush, just a tiny bit more. I think we're there. And what I want to show you is that even with the special tool installed, I've knocked the girdle spring out. So let me see if I can zoom in here enough that you can see that spring. Is that good enough? So I've knocked the girdle spring out. I'm going to have to get a pick and roll that back in, which can be done, but it's that impact of hitting the hitting that seal to drive it in that can knock that girdle spring out. And the purpose of that girdle spring is to keep a squeeze force on that seal, so when it rides on the pinion, let me zoom out here just a little bit. When it rides on the pinion flange that fits down in there, it won't leak oil. So let's zoom back in. The spring that we did not want to knock out is right there. So that's a problem. So we're going to have to use some picks to get in there and carefully work that back into place. Okay, so what I had to do to get that girdle spring back in was to take a couple of 90-degree picks and just start on one side with both picks and just work my way around in each direction in a circle while pulling up, and it popped back in. So our girdle spring is reinstalled. You always have to watch for that. Sometimes it can be a real pain, real inconvenience, but you don't want an oil leak, so you got to make sure that that's in there. So now that we've got the pinion oil seal installed and the front pinion bearing installed, we are ready to put the pinion gear in, and we will have to once again drive the bearing down onto the pinion shaft itself to do that. So let me grab the tube and a hammer. There's one other thing I almost forgot, and that is before we put this pinion gear in, these splines right here need to be coated with some sort of Teflon pipe sealant, like you would use to seal water pipes or house related piping. And so this is kind of an older can, but it's pretty thick. It's got a little paintbrush there, but I'm going to paint this on to, if it'll, wow, yeah, it will. It'll stick, and work this into these splines here. I probably ought to get a newer can of it for the future. This is thickened up quite a lot, but I can just work it in by hand. Here. And once again, the purpose of this is to help prevent oil from wicking or working itself up these splines and leaking out in that oil sill area. Makes a lot of technicians think the oil sill is leaking, but in fact it's the splines having oil come up and out. And that's especially true if your vent for your differential is blocked. Maybe it's really dirty, covered with mud, undercoating, whatever you may have there. Just find your vent and make sure that it's free and unobstructed. Okay, so I've got a really thick coating of the Teflon pipe sealant installed there on those splines, and that way when we put our flange down on, it will have some sealing take place. Let me take off some of that excess. We don't need that much on there. We don't want it to get into our bearing, cause problems. Alright, I think that'll do the trick. So we're going to take the pinion with the crush sleeve and put it up through the bottom here. And put it up through that upper bearing. But the upper bearing is a press fit onto that pinion shaft. So we have to come in. You could do it with the flange, but I happen to have the pipe here that installed the pinion rear bearing, and I'm just going to lightly tap on this pipe to try to drive that bearing I'm checking to make sure I still have free play. I still have free play, end play there, so we're not destroying bearings, pounding on them. If you don't, obviously, if you don't have a pipe the right diameter, use your pinion flange. Get it lined up and get a block of wood and put the wood on top here so you're not hitting the flange itself, and drive it down that way. Drive the bearing down and the flange down at the same time. Now I need to drive this flange down a little bit more so I can get the pinion nut on. So let me grab a block of wood here real quick. So I'm just going to put this 2x4 across the top of the flange area here. I'm going to reach up underneath and grab that pinion gear and push up with it, and then just drive this pinion flange down until there's enough threads that I can get the pinion nut on with 3 or 4 threads showing. There we go. It usually goes on pretty easily. It's a little tight because it's a brand new set of gears and the splines don't have any wear at all in them, which is great. It just makes everything tighter. So you can now see that we have the threads of the pinion gear sticking through the pinion flange, and I'm going to take the flat washer that goes with the pinion nut. Here we go. So we've got this flat washer that we have to install, so I'll put that on right there. And then I've got the new pinion nut that I want to install also. But this is a mechanical locking pinion nut, but just to make sure, I'm also going to add some Loctite red thread locker, the 271 thread lock, to it. So let me grab that real quick. You're always going to need a variety of thread locking compounds when you work on axles, and there's different strengths, there's different temperatures at which it melts. It's all kinds of options for you, but if both surfaces are clean and dry, then we can put the Loctite on. This Loctite is, once again, the 271 red Loctite. It's meant to put on things that you hope you will never ever have to take apart again. So I'm going to just put a little bit on there. Keep the cap locked tight on that, and then we'll take our nut here and start to roll it down. That little indentation in the nut right there is a punch mark where it'll get harder to turn here in just a moment, because it's a locking point. So just right there, I've hit those threads to where it does not want to rotate easily anymore, because the threads are not round, because they've put that punch mark in there to act as a lock. But I prefer the red Loctite in addition to that. So we're going to have to hook up the pinion flange holding tool and then get our ratchet and socket out to tighten this nut down. Now remember, this time we have to crush the crush sleeve besides setting the bearing preload to the proper 15 to 25 inch-pounds of rotational torque. Okay, we are ready to tighten the pinion nut down again. And if you recall from the first video, the disassembly video, the part 1 video of this series of 4 videos, it was oh, actually that was the, yeah. We, on disassembly, we used this blue tool to hold the flange from rotating, and then just used a long ratchet and a 1 1/8 inch socket here to turn that nut. In the earlier part of this video, when we started tightening down the old pinion nut, if you recall, I put in the old pinion nut on our trial installation. I started tightening the nut, and I reached a point where it became real obvious, like right there, that something had changed, and that's where the upper and lower bearings had contacted the bearing cups, bearing races, and anything tighter than that would be preload. Well, now that we have the crush sleeve in, typically at this point we are not in preload territory yet. Usually there's some up and down play right here, so let me see if we have some up and down play. Yes, we do. So here's, we're at the point where the crush sleeve is going to make things harder for us. I'm right here ready to tighten this tighter, but I'm at the point where all the free play in the or all the spacing between the pinion bearings is taken up with that crush sleeve, but yet we still have end play. So to be able to get rid of that end play and then get to a point where we preload the bearings, we have to actually physically crush that crush sleeve. Now, this is where most technicians will give up and grab an air gun and just rattle and hope that they get it right. But it's almost impossible to get it any tighter at this point. If I try to tighten this up anymore, that's about the limit of my strength right there, and I still have up and down play in this flange in the pinion gear. So this thing is not ready to continue going together until we get rid of that play and set the bearing preload. So the way that I do that is with what's called a torque multiplier, and I'll show you that here in a minute. But other people may just get a pipe and put on the end of their ratchet. I've got this is a 1/2 inch drive ratchet. I've got a 3/4 inch drive ratchet with a 4-foot handle. But then that 4-foot handle ends up being longer than this blue special tool to hold the flange, and so then you're fighting each other. The blue bar is fighting the longer handle for the most leverage, and so what we end up doing here is turning this flange, or turning this axle housing in the holding fixture on its side. So let me get it positioned on its side, and when it's on its side, then this holding fixture can lay against the bench as we tighten the nut with a longer bar with more leverage, and that will allow us to let the table do all the hard work. And so let me get that set up, and we'll try it. Okay, I've got the axle housing rotated in this holding fixture. I've got this blue axle or pinion flange holding tool laying against the workbench here. So now if I come in with a socket and ratchet, and I've got a 3/4 inch ratchet here with a 3/4 inch drive socket, 1 1/8. This thing has a 4-foot handle. So for guys like me that don't have a lot of physical strength, we can take advantage of leverage. It works very well. And So we'll put that on, and we can turn the nut. Let me come out here on the end of our 4-foot bar with the leverage, and where I could not turn the nut before, now I can. But it's still a lot of work. We're crushing that crush sleeve, and for most of you, this is probably something like what you're going to end up doing, is either with a pipe on the end of a breaker bar, turning this flange, or you've got to hold the flange still and turn the nut. And this can work, but you've got to be careful, because once again, we're concerned with taking the free play, and there's still free play, back and forth play in the pinion bearings there. We've got to turn that nut until that free play's gone. Well, most of you probably aren't going to have a holding fixture like this. You might could just make one, cut one out of I don't know what to tell you to hold this without having the proper tool. So most techs, since they either can't find or won't bother to look for or don't have this special tool, which works for just about any brand or any year of axle, it's well worth purchasing. They will just grab the air gun and rat-a-tat-tat, fill for end play, rat-a-tat, fill for end play, and you might get lucky, but all that impacting that an air impact gun does can be really hard on bearings. And if the ring gear were in there at the same time, you would have gears slamming on each other, which could chip gear teeth and cause damage also. So this, remember, the service manual told us it could take up to 350 foot-pounds of torque to start crushing that crush sleeve. Well, 350 pounds for 1 foot would be the same as 175 pounds for 2 feet, and I've got a 4-foot long bar, so that'd be 87.5 pounds of force I would have to put on the end of this 4-foot ratchet to continue turning this this nut. But for me here at the school, I have actually an easier way to do it, and it does not involve an impact gun. It involves another tool right here, and this tool is about, I think it's around $175. This is from Snap-on. This is called a torque multiplier, and it has a planetary gear set in the head here that we are turning, let's see, we're probably turning the planet carrier, and then let me see, yeah, and then the ring gear is the part that is responding, but it takes 4 rotations of this side to equal 1 rotation of this side. That's why it's called a 4-to-1 torque multiplier. So theoretically, if you put 25 pounds of input torque on this side, it would deliver 100 foot-pounds of input torque on the other side, or output torque. But the label here says that even though it's a 4-to-1 gear ratio, you need to allow about 20% loss because of the friction in the gears, and so it's not quite exactly 4-to-1, but what it does do is it makes it about 3.7 times easier to turn this pinion nut than it is without one of these tools. So now if I turn this back to the upward position, we'll see if I can do it with just the torque multiplier. So we'll get that locked into place. We'll take our extension and socket off the ratchet here. So the output drive of the torque multiplier is 3/4 inch drive. So I'm going to put this 3/4 inch drive, 1 1/8 inch socket down on that pinion nut. I'm going to put that over here by the by this blue flange holding fixture, pinion flange holding fixture tool. And then we've got this little bar that has the rectangular hole in it that'll work with the blue tool, and the round hole in it that'll work with the torque multiplier. So I'm going to, as you can see, I'm going to bring that up and put that right up in here, and that bar is going to lock those two tools together because they are going to want to go opposite directions when we start rotating this. Then I'm going to come in, because the input on the top here is a 1/2 inch drive. I'm going to take my 1/2 inch drive long ratchet and put it on here. This is a 36 inch ratchet. We've got a 4-to-1 torque multiplier. This gives us 3-to-1 leverage, and so this should be approximately let's see, it would be 12 times easier if these were only 1 foot long, but they're 2 feet long, so roughly 6 times easier to turn this nut with this torque multiplier setup. And this is only a 4-to-1 torque multiplier. They make a 16-to-1, they make a 64-to-1, and of course they're much more money, but a 4-to-1 is all I've ever needed to tighten pinion nuts. So let's see if this old guy in a wheelchair can crush a crush sleeve. So we're turning, but since it's a 4-to-1 multiplication, it turns gear reduction, it turns very slowly. I have to stop and check to make sure that we still have up and down play, which we do. So let's keep going. Let me check it again. We still do. This can take a while because of the 4-to-1 multiplication, and I'm not turning huge increments of rotation here, but notice I'm turning it just fine. Oh, it got harder right there, and that usually means our bearings have hit. Oh, there's still just a tiny bit of free play, end play there. Usually when there's an obvious difference, something is happening, something's taking up clearance. Okay. Now let's see if we have up and down play. Just maybe a tiny bit. Now keep in mind we're crushing that crush sleeve. I'm applying more than 350 foot-pounds of torque through this torque multiplier with just a 1/2 inch ratchet and this holding fixture. Work smart, not hard. Okay. There is no up and down play there. Excuse me. So the question I have now is, do we have bearing preload yet. And the only way to find out is to measure it with the inch-pound torque wrench. But I like to rotate this tool around to make sure those roller taper bearings get seated there. And let me just double check again. Now I think there's still a tiny bit of play. And maybe there was no play before I rotated it. That's why we rotate these, is to make sure that we get the free play. Get those bearings seated and get the free play out of it. Okay, so let's see. Still spins kind of freely. Remember when we took this apart and we gave it a little bit of a spin, it didn't keep going like that. So let me tighten it just a little bit more. It may look like I'm doing a lot of turning here, but remember, it's that 4-to-1 reduction. I'm only turning a... Ooh, there we go. Look at that. Okay. So, let me rotate it around a couple more times just to make sure that the bearings are seated. Pull this holding tool off. Get our torque multiplier out. And let's take this tool off of here and see how much rotational torque we have. Now here's the the tricky part, the scary part almost, is if you've gone too far, if you've overdone it. If we exceed 15 to 25 inch-pounds of rotational torque here, we have to take this whole thing apart again, replace the crush sleeve. We're going to ruin that seal, the pinion seal that we just drove in. We've got to get that out, and we need another pinion nut to lock it in place. So hopefully that is not the case, because I don't have replacements for any of those. We'd have to order them. So we have to be very careful, take little tiny baby steps as we tighten this down. So let me set our 0 to 30 inch-pound rotational torque wrench up here and give it a rotation. Feels good, nice smooth bearings. And as we pull that off of there, we are at 12. So we're below the 15 to 25, but that's better than being above by far. So let's put the tool back on. We need to tighten it just a little bit more. Got to have patience. Got to turn it just a little increment at a time, because it's worth being patient doing that, because it'll take a lot more time to tear this whole thing apart and go find seal and crush sleeve again. So be patient when you're doing your own axle, or you'll mess it up and have to go get new parts. As a matter of fact, you may want to just order an extra crush sleeve and an extra seal, just because for most of you it'll be your first time doing it, and chances are really high that you're going to mess it up. No offense, but it's I've taught too many classes with beginners that almost every single beginner messes it up. So let's put our torque multiplier back on. our little holding tool. Oh, great. Got oil on it. Get that held in place, and we'll grab the ratchet. And the temptation is to give it a big turn. A lot of techs or students I've seen at this point will try to give this ratchet a like a quarter of a turn here, but I'm not going to do that. I'm going to do maybe just less than an eighth of a turn, just like that. That's as far as I'm going right there. So then we'll rotate it around, take the tool off. Love the torque multiplier. Okay, here we go. Let's see if we've gone too far. It doesn't take much to go too far. So we've got it zeroed. We'll crank it around here. Oh, we are good. That is 18. So let me get up somewhat closer here to where it's readable. The silver pointer is on the black scale, 18 inch-pounds of rotational torque. You can't ask for anything better than that. So we went up 5 foot or 5 inch-pounds of rotational torque with less than an eighth of a turn on that 4-to-1 torque multiplier. As you can see, one of those torque multipliers, if you're doing a lot of this type of work, is well worth the purchase. So we've got a good seal. We've got the Teflon sealing on the splines. We've got a new nut. We've got Loctite on it. We've got good bearing preload. All we have to do to finish this axle up is turn this housing over, put that differential case back in, and set the backlash to 7 to 9 thousandths of an inch. We know our contact pattern will be right on the money at that point, because that's exactly where we had it yesterday. And torque those bearing caps down, double check our total turning preload to make sure we got that right. And this thing's ready to go back in the vehicle at that point. So let me grab the differential case, and we'll get that installed. Lost my remote. Okay, so we're going to just set this differential case back down in where it was on our trial run. I'm going to take the threaded spacer from the right hand side and get it started. There we go. I made a mark on the threaded spacer here to allow me to see where it was versus the old or versus our old position when with the bearing cap on. You'll see when I put it back together, because theoretically if we put this right back where it was, our contact pattern should be the same, our bearing preload should be the same. Okay, sorry, my battery pack died for the camera. I had to swap that out. So we had just installed this rotating spacer, bearing spacer on the right hand side. Got the one for the left hand side. I also have a mark on it to help me see where it was in relationship to the bearing cap the last time I had it apart. There we go. Okay, and then if you remember from the instructions in the service manual, it told us to tighten the left-hand bearing cap until there was no play, no end play. So we can't tighten the left-hand one without loosening the right-hand one, which is what I'm doing there. Still have play. Oop. We passed the zero play part. Got some play. Play. No play. Right there. Okay. And as it turns out, my alignment mark on this left-hand side is exactly where it was when I took it apart. My alignment mark on this side, as you can see, is down here. So right down there is my alignment mark. Let me bring it up here just a little bit, right here. And that's going to end up having to come clear up to this position here. So I've got to get the bearing caps put on now. And as I mentioned, the trick to that is to start the bolts first. Have the adjustable nuts just a little bit loose, but start the bolts. And then once they're started, just lightly tap down. Make sure that the threaded adjuster can still rotate, and if it does, then we must be lined up properly. And we'll do the same thing here on the other side. Get the bolts started. There we go. Tap it down. Threaded adjuster still turns. So let me get these bolts down, but not torqued all the way. We'll just get them down to get the play out of them. All right, I've got the free play out of the bearing cap bolts, and we're ready to go through the adjustment procedure on the adjustable sleeves here. So once again, the instructions were take the free play out of the backlash. Right there is where my alignment marks line up on the left-hand side, or the left-hand side, the driver's side. And then it said to tighten this right-hand side while rotating the pinion, or the ring gear, to take the slack out of the bearings, take the play out of the bearings. So snug it up, back it off, snug it up again, and then it said to tighten it 2 more notches. Well, here's my alignment mark, here's 1, 2 notches. If we put my alignment mark right back where it was when we disassembled this after our trial assembly, then our pinion depth, our or side bearing preload, our total preload, our backlash, all of that should be exactly the same. So let's get those marks lined up, and we're not going to take it for granted that everything's lined up and perfect. We're gonna measure it again, but right there. The mark's almost lined up, just a tiny bit more. There we go. Okay, so the next step is to tighten the bearing caps down to their specified torque, which was 70 to 75 foot-pounds. So as I did yesterday, I'm just going to tighten these to 70 foot-pounds. Keep the table from rolling away. Went up to 73 on that one, went too far, got the red light on. But 70 to 75 is the spec, so we're still okay. And 70. Okay, so we have, theoretically, at this point, everything is identical to how it was before, when we set it up with no crush sleeve and no pinion seal. Everything should be exactly the same, which means if we turn this over and measure the total turning preload, what did we have? Yesterday we had 50. Oh, it won't be the same because our pinion preload is a little bit higher this time. We had exactly 15 bearing preload before on the pinion, but this time we had 18. But we had 26 foot-pounds of bearing preload on the side bearings. That should not have changed. Of course, the 26 was divided by the 336 gear ratio. So let's go through that again. Let me grab the torque wrench here. And we're going to expect to see more than 15 or the 18 inch-pounds, because that's the pinion alone. So let me rotate it around. All right, I am reading 27 on the maximum dial here. 18 of that is the pinion. So 27 subtract 18 is 9. So if I take my calculator here, 27 subtract, well, 27 total turning preload. That's everything combined. Subtract the 18 that we had for the pinion. That leaves us 9. Now we multiply it by the gear ratio, so times 3.36. And we do that because turning the pinion is 3.36 times easier than turning the ring. That gives us a side bearing preload of 33.48. The specification is 25 to 35. We are at 33.48. So this is right on the money, perfect for bearing preloads, for pinion preload, for pinion depth. And the only thing we have left, the two things we have left to do are check the backlash.